Kelsey Christensen.
And I'm Cindy Gow. And our topic is on Einstein's theory of relativity. Relativity is a tricky subject because it requires hours of careful thought, an open mind, and also a dark room to cry in, just in case it gets really confusing.
We'd like to set the scene for you guys. Okay, so first, me and Cindy decided that we wanted to do Einstein's theory, or special theory of relativity, because we were sitting in the classroom, and at first we wanted to do DQ, and then we found out that someone had done that previously, and we were like, God, we really want to do something that no one's ever done before, something that we can teach the whole class, something that we've never talked about before. And so we looked this up, and we were like, God, this is so mind-blowing, we have to show the whole class. So that's kind of how we decided to do special relativity.
Just some background information, Albert Einstein discovered the special theory of relativity in 1905 and then later found more of a general theory in 1915.
Okay, so you guys are probably wondering what is special relativity and what makes it special. And special relativity applies to inertial objects, which in simple terms means that it applies to something that is stationary or something that is at a constant speed. And can someone raise their hand and tell me how they know that they're moving? Yes, Quinlan.
I know I'm moving when I'm in one place and then I end up in another place after.
Anyone else? Yeah.
You have to reference the items around you to see that you're moving.
Very good. So what Einstein pretty much said is if we were floating in space and there was absolutely nothing around us, how would you know if you're moving? If a meteor is coming towards you, how do you know that it's coming towards you? What if you're going towards it? How do you know you're moving out of the way? This was an incredible discovery.
And then general theory of relativity is Einstein spent 10 years trying to include acceleration in the theory and published his general relativity in 1950. In it, he determined that the massive objects cause a distortion in space and time, which is felt as gravity.
So Einstein's theory of general relativity predicted that the space-time around Earth would not only be warped, but also twisted by the planet's rotation. So in the big scheme of things, so general is different than the specific relativity, and in general relativity, it's pretty much saying the gravity or the gravitational pull that we feel on Earth is due to the curvatures of space. Yeah, so that's pretty awesome.
And then here we have that just kind of like gives you like a visual image. Why do they call it special? It's special because it only deals with simple systems. Systems where things are moving in a nice straight line and are at nice constant velocities. So there's no forces, no acceleration, and Einstein developed two postulates for special relativity. All physical laws are the same at whatever constant velocity you are moving at, and then the speed of light is always the same, independent of the motion of the observer or the light source. So light is always moving at the same time. Like, speed of light can't change.
To add on to that, they made this discovery. They were doing tests to see if they could have like a reference point on how do you tell how your velocity on something that's stationary and how do you compare it. And so they found that no matter what way the person is looking at the speed of light, it's always going at the same constant speed. So like, we'll get into that more when we have more videos, but it's pretty cool. Okay, so this is me and Cindy at our local shields or the escalators.
We decided to conduct an experiment and an example for you guys to see.
So in here we talked to the shields manager and found that the escalators are going at the speed of 3 miles per hour. So I am the constant or the non-moving object, and Cindy is approaching me at 3 miles per hour, and she looks like she's approaching me at 3 miles per hour from where I'm standing. Now, Cindy is the constant right there, and we found that the average walking speed of a person is also 3 miles per hour. So relative to Cindy, I look like I'm walking 6 miles per hour, but I can say that I'm only walking 3 miles per hour. Cindy is walking up the down escalators. Relative to me, it looks like Cindy's not moving at all, and she just looks ridiculous walking up the down escalators. But Cindy can still say that she is walking at a speed of 3 miles per hour.
People kept giving me funny looks.
We literally had to take this like 5 times. So.
So we decided to build a time machine. In here, as you can see, this little thing is a clock. So our clock, it has 2 panels, one on top and one on bottom, and in between there's a marble that clicks in between them, and every time it clicks, that's just like a second. So it's kind of like a weird clock. And if I'm in the rocket ship and I have this clock, I can see that it's moving up and down. But then, once the rocket starts moving, I still see that it's moving straight up and down. But if Kelsey was watching me from a distance, she would see that my clock is not moving up and down. It would be moving at a diagonal because my clock would be moving like that in the other rotation.
So it's like saying if I was just standing here and Cindy was walking past me with her clock, if Cindy is staring at her clock, it still looks like the marble's going up and down, but if we did a slow motion of Cindy walking past me, you would see the clock moving at this little...
Have you ever seen like, I don't even know what commercial it is. I think it's like a Gatorade video or a commercial where they take a bunch of photos, but it's like time frame photos, and you can see them moving, but it's all just photos. That's basically what this is.
We have a nice little video that really helped us through this project.
One is you stationary on Earth, and one is your twin zooming by in a rocket. You have identical clocks. Let's look at yours first. Each time light makes a round trip in your clock, you count by 1. Your twin will measure the same rate on her own clock. Now, things get weird when you watch her clock. Because of her sideways motion, you see that her light has to travel a longer distance for 1 tick. And since the speed of light is the same for all observers, her round-trip ticks must take more time.
So time actually ticks slower on her moving rocket according to you, stationary on Earth. And this is a real phenomenon. It's not some weird mind trick. We don't usually notice this though because time dilation is quite insignificant until you're moving close to the speed of light. So now, from your twin's perspective, you are moving.
Therefore, your clock must be running slower according to your twin. And because the laws of physics are the same in both of these frames, yours and hers, each frame is equally correct in saying the other's clock is running slower.
This is where the paradox starts. Imagine you and your twin start off on Earth.
You stay here, but your twin zooms off in a spaceship at half the speed of light, turns around, and comes back. The whole trip takes 30 years, but you see your twin's clock tick slower.
So, due to time dilation during the journey, she only aged 26 years, 4 years less than you. Now, here's the crux of the problem. From your twin's perspective, she was stationary, and you, on Earth, moved away and came back.
You're the one moving at half the speed of light. So your twin should see your clock going slower and should think you are only 26 years older by the end of the trip.
So yeah, that's not possible. When your twin gets back, she's either younger or she's older. She can't be in a superposition of both. This isn't quantum. So how do we solve this paradox? Well, the answer lies in the details. When your twin turns around, she has to accelerate, which means she's no longer in an inertial reference frame while she accelerates, and so special relativity no longer applies to her. It's not as simple as saying your twin sees you make a round trip and you see your twin make a round trip. It's not a symmetric problem like that.
Because when your twin accelerates, we can tell the difference between the physics that might happen in those 2 frames.
She will feel the acceleration during the turnaround, and you will not. So when she gets back, she will agree with you that you are 30 and she is 26.
No, pretty crazy. Oh yeah.
Okay, I'm gonna write something on the board in just a second. But here we came up using simple trigonometry to create a rest frame equation, and we used the delta t, a simple distance over speed calculation, to measure the time between clicks on the rest frame. And then when moving along at a constant speed, v, the situation will be in this situation right here.
You can erase, if you need to, I don't know if you have anything to erase. There's a cloth there if you need to erase.
Good. Okay, so the time between clicks, we would use the integral for distance over speed. And then using Pythagoras' law for right triangles, we can calculate the distance, where we call L, use L for the height, and the length across the bottom is how far the clock has moved in one click. With this. So that's like the basic distance formula. So this would be the height, and this is the length across the bottom. And so next, we substitute the expression for d and rearrange it and simplify for. And then z is just the constant. So this is the equation for time dilation, and this tells you how much the moving clock, which is this, will differ from the resting clock, which is just the basic. So since the difference is so close to 1, we can't detect that there is any difference at all. That's why people think that we're moving at the same time, and that's why people get so confused on relativity, because we don't know when we're moving and when we aren't. And so an example would be, like the video said in the second problem, where two people have synchronized watches. One person will travel at 120 miles per hour, and that person is stationed. But if another person is moving, they will get 29.999 seconds, but the stationary person will get 30 seconds. And since the difference is so small, it's so hard to measure even with the best technology. And we'll see a little further on.
Okay, so and then I have a handy cool equation for you guys. Let me just pull it down and show you, and I'll write the equation. I'll hold it here. Okay. Oh, perfect. Okay, so how fast must a rocket travel to another faraway planet? So that means that it's always in a constant speed. So in the video it said that the law of special relativity did not apply to it because it changed direction, correct? So if I'm going at a constant speed to a faraway planet, how fast must the rocket that I'm on be going for me to age only 10 years, while Cindy, who is back on the planet Earth, stationary, ages 100 years? All right. All right. So we have 2 times. We have 10 years and 100 years. And these will be both represented. This one will, let's just say this one will be delta t, and this one will be delta capital T, T for time. And then so we'll do delta small t equals delta big T all over the square root of 1 minus b over c squared. First, okay, so I have to describe this a little better. Once, after my 12 hours and 48 minutes of watching videos on how to understand this, I found the best way to understand an equation like this is to draw a graph first. So I'll draw this. And this will be like our rocket, so I'll name it R. And then we're trying to find the velocity as, so we're trying to find V. And then this one will be this 10 V. this will be planet Earth, and t will equal 100 years. Okay, so you guys are probably wondering why you do 1 minus this, and you find that, so the speed of light, when you want to graph that, is you always want to do it to 1 just because it's easier. So you want to do a 45-degree angle going out like this. And when the line is going out this way, so it's increasing or it's like positive, that'll be the x minus t. And then if you drew this graph like this, and this doesn't get into like the advanced stuff, but if you ever did like where it went off this way, this would be the x plus t. But don't worry about that. You don't need to worry about that. We just need to worry about the x minus t. So back to our equation. So then you just use simple math to figure this out. And I'm going to multiply each side by square root of 1 minus b over c squared. So then it crosses this out, and then multiply 1 minus b over c squared. So then big T, and you divide by delta T, you get the square root of 1 minus T over C squared equals big T over little t. Okay, so then once you get it this far, it's kind of easy because then you just plug in the equation. So then we go back here, and the little t is 10 years, and the big T is 100 years. So what you do?
Tenth graders are now released for locker cleanout. Tenth graders are now released for locker cleanout. Thank you.
Because, like I said previously, you always, in your equations, you want to make the speed of light equal to 1. And so if you did 100 over 10, that'd be clearly over 1. So the little t would always have to be bigger than the big T. Okay. So then we get, oh jeez. Okay, so we get negative 1 over c squared. And then, okay, 0.1. And then because we're trying to solve for v, right? We're still trying to find that velocity. So in order to get rid of the square root, you just square each side, and you get oh, 1, subtract 1, and you get that equal 0.9. And since they're both negatives, then you just multiply by negative. This is kind of taking up a lot, I'm sorry. Then you get b c squared equals 0.99. And then you want to find the square root again. So then you get b c equals 0.9. 7, and multiply by c, and your velocity, or my velocity on the rocket would have to be 0.99487 c, and c stands for the speed of light. So you have to be going extremely fast.
And then to add to that, so at low speeds compared to the speed of light, it's hard to notice the effects of relativity because it's so fast.
Like here's an example. When you guys are in a car, I hate this. Hold it down. Not all the way down.
Perfect.
So when you guys are in a car, right, you can eat stuff, you can drink something without it spilling all over you. Have you ever wondered why that is, that you can be in a moving object and you aren't spilling anything, or it's not like flying out of the car? It's because relative to the car, if you're looking down at your feet, you can't tell you're moving until you look to the side of you and you're moving. So all of the objects inside of that car are going the same speed as you, so you don't realize your speed that you're
So
going.
basically, if you're holding that apple is going 50 miles an hour. But when you're looking at it, it's just sitting in your hand. But if I was like standing on the road and I watched that car drive by, I could see the apple flying 50 miles an hour.
Click. Okay, so the other applications that you can do this for, planes, cars, train rides. GPS actually is a huge thing of this because when you're in the GPS, it finds your location relative to the planner. So, it's like getting in my mouth. So a funny one. You could find, let's say an old man falls down the stairs with a ball in his hand. You could find his relative velocity compared to the lady that is standing atop the stairs watching him as he falls, compared to the ball. So, we'd really like to appreciate your time and sticking with us because this is a big topic and it probably got confusing, but we'd like to open up this time for any questions that you may have.
Well, I think a round of